This is everything weird about mathematics. The history, the paradoxes, the moments where the rules broke down, and the places where even the smartest people who ever lived had to sit down and admit they had no idea what was going on. And at the end, we are going to look at some of the strangest unsolved problems still sitting on the table right now. Let's begin. Mathematics is supposed to be the one thing humans got right, the one discipline where there is no debate, no interpretation, no room for opinion. 2 plus 2 equals 4. It always has. It always will. No culture, no civilization, no alien intelligence anywhere in the universe is going to look at that and disagree. And that certainty, that absolute locked-in reliability, is exactly what makes mathematics so useful and so trusted. But here's the thing. The deeper you go into mathematics, the weirder it gets. Not weird in a loose or metaphorical sense. Weird in the sense that trained mathematicians, people who had dedicated their entire lives to the subject, encountered ideas that made no sense, results that seemed impossible, and logical conclusions so disturbing that some of them refused to accept them. One of the greatest mathematicians of the 19th century had a mental breakdown partly triggered by the implications of his own work. Another spent decades trying to prove that a branch of mathematics he had helped invent was actually nonsense. Another produced a theorem so devastating to the foundations of the subject that it essentially proved mathematics could never fully understand itself. These are not fringe stories. These are not the cautionary tales of people who wandered too far outside the mainstream. These are the people who defined the mainstream, and what they found when they went deep enough was that mathematics is stranger than anyone had expected. That is what this is about. We are going to start at the beginning, not with the weird stuff, but with the moment mathematics first showed up and why it showed up the way it did. Because the strangeness does not come from nowhere. It grows out of something very ordinary, humans counting things, and the path from counting sheep in ancient Mesopotamia to a theorem that breaks the foundations of logic is a straight line. It just takes about 4,000 years to travel. So lie down. This is going to be a while. Infinity's paradoxes. Imagine you are Georg Cantor. It is the 1870s. You are a mathematician working in Halle, Germany, and you have just decided to do something that essentially no serious mathematician before you had been willing to do. You are going to treat infinity as a mathematical object, not as a concept, not as a philosophical idea, not as shorthand for something that keeps growing without stopping. As an actual thing that can be measured, compared, and reasoned about with the same rigor as any other number. Everyone around you thinks this is a mistake, not because they are small-minded, because for 2,000 years the greatest mathematical thinkers in history had looked at infinity and collectively agreed that the safest thing to do was to treat it as a limit, a direction you could approach but never actually reach. Aristotle had drawn a firm line between what he called potential infinity, something that could keep growing forever, and actual infinity, a completed infinite thing that simply exists. Aristotle said potential infinity was fine. Actual infinity was not a coherent idea, and for roughly 2 millennia mathematics more or less agreed with him. Cantor disagreed. And what he found when he started pulling on that thread did not just change mathematics, it cracked the foundation. Here is where it starts. Cantor wanted to compare the sizes of infinite sets. A set is just a collection of things. The set of all natural numbers, meaning 1, 2, 3, 4, and so on forever, is infinite. The set of all even numbers, meaning 2, 4, 6, 8, and so on forever, is also infinite. Common sense says the first set should be bigger. After all, the natural numbers contain all the even numbers plus all the odd numbers. It should be twice as large. Cantor said that common sense was wrong. His reasoning was this: two sets are the same size if you compare every element of one set with exactly one element of the other set, with nothing left over on either side. Mathematicians call this a one-to-one correspondence. If you can build that pairing, the sets are the same size. It does not matter what the elements look like. It does not matter how the sets are defined. The pairing is everything. So take the natural numbers and the even numbers. Can you pair them up perfectly? Yes. Pair 1 with 2, pair 2 with 4, pair 3 with 6, pair 4 with 8. Keep going. Every natural number gets paired with exactly one even number, and every even number gets paired with exactly one natural number. The pairing works perfectly, and it never runs out on either side. Therefore, by Cantor's definition, the set of natural numbers and the set of even numbers are exactly the same size. The set of all natural numbers is not larger than the set of all even numbers. They are equal. Even though one contains the other, this is already strange, but Cantor was just getting started. He then looked at the set of all rational numbers. Rational numbers are any number that can be expressed as a fraction, 1/2, 3/4, 17 divided by 5, and so on. There are infinitely many rational numbers between 0 and 1 alone. Between 0 and 1/2, there are infinitely many more. Between any two rational numbers, no matter how close together, there are always infinitely many others sitting in between. Surely this set must be larger than the natural numbers. Cantor showed it was not. He invented a technique now called Cantor's diagonal argument, or in this case, his pairing technique for rationals, where he demonstrated that you could arrange all rational numbers in a grid and then trace through that grid in a specific zigzag path that would allow you to pair every rational number with exactly one natural number. The pairing works. The sets are the same size. He called this size Aleph null, the first and smallest infinity. Then he looked at the real numbers. Real numbers include everything, not just fractions, but also irrational numbers like the square root of 2, and transcendental numbers like pi and e, the full continuous number line, every point on it, every decimal expansion that ever existed. And here is where the ceiling fell in. Cantor proved that you cannot pair the real numbers with the natural numbers. No matter how clever your pairing system is, no matter what method you use, there will always be real numbers left over. The set of real numbers is strictly, provably, irreducibly larger than the set of natural numbers. There is no one-to-one correspondence. The pairing breaks, and this means there are at least two different sizes of infinity, Aleph null, the infinity of the natural numbers, and a strictly larger infinity, the infinity of the real numbers, which Cantor called the cardinality of the continuum. The proof he used to show this is one of the most elegant arguments in all of mathematics. Assume you have a list that supposedly contains every real number between 0 and 1, every single one, written out as an infinite decimal. Cantor says, take the first digit of the first number and change it. Take the second digit of the second number and change it. Take the third digit of the third number and change it. Keep going forever. You have now constructed a new number that differs from the first number in its first digit, differs from the second number in its second digit, differs from the third number in its third digit, and so on forever. This number is not on your list. It cannot be because it disagrees with every single entry on the list in at least one position, but your list was supposed to contain everything. Contradiction. The lists cannot exist. The real numbers cannot be paired with the natural numbers. The infinity of the real numbers is larger. This result broke people, not figuratively. Henri Poincaré, one of the greatest mathematicians alive at the time, called Cantor's work a disease from which mathematics would one day recover. Leopold Kronecker, who had been one of Cantor's own teachers, called him a corrupter of youth and spent years trying to have him professionally destroyed. The attacks were sustained, personal, and vicious in a way that is almost unrecognizable in modern academic discourse. Cantor suffered multiple mental breakdowns. He spent significant portions of his later life in a sanatorium. He died there in 1918, largely convinced that his work had been a failure and that he had been abandoned by the mathematical community. He had not failed. He had been right about everything. David Hilbert, who is widely considered the greatest mathematician of the early 20th century, said this about Cantor's work. No one shall expel us from the paradise that Cantor has created. It was a full vindication, but it came too late for Cantor to properly hear it. Here is what makes this more than just a historical tragedy. The implications of what Cantor found did not stop at the boundary of set theory. They reached into the foundations of all of mathematics. If there are multiple sizes of infinity, and if the real numbers represent a strictly larger infinity than the natural numbers, then a question immediately follows. Is there an infinity that sits in between, something larger than Aleph null but smaller than the cardinality of the continuum? Cantor believed the answer was no. He called this belief the continuum hypothesis. He spent the rest of his life trying to prove it and could not. It became one of the most famous unsolved problems in mathematics. In 1900, Hilbert listed it as the very first problem on his famous list of the 23 most important unsolved problems in mathematics. The first one out of 23. In 1940, Kurt Gödel showed that the continuum hypothesis cannot be disproved from the standard axioms of mathematics. In 1963, Paul Cohen showed that it also cannot be proved from those same axioms. Together, their results mean the continuum hypothesis is independent of the foundations of mathematics. It is neither true nor false within the standard system. It is simply undecidable, which means the question Cantor devoted his life to and lost his mind over is not just unanswered, it is unanswerable, at least from within the mathematical framework we have. That is where the story of infinity currently stands. We know there are multiple sizes. We know the real numbers are strictly larger than the natural numbers. We know there is almost certainly an infinite hierarchy of larger and larger infinities stretching upward without limit. And we cannot determine whether the first step in that hierarchy, the gap between the smallest infinity and the infinity of the real numbers, contains anything at all. Cantor opened a door, we walked through it, and on the other side we found not answers, but a larger and stranger darkness than the one we had been standing in before. Zero's chaos. Picture a 6th century India. You have just done something that sounds trivially simple and will turn out to be one of the most consequential decisions in the history of human thought. You have given nothing a name, not nothing in the philosophical sense, not the void, not the absence of being, not the silence between words. You have given the empty column in a counting system a symbol, a placeholder, a number. You have said that the absence of quantity is itself a quantity and that it deserves to sit on the number line alongside 1 and 2 and 3 as a full and legitimate member of this system. The symbol was a small dot. The mathematician was Brahmagupta. The year was approximately 628 of the Common Era, and the decision to treat 0 as a number rather than as a mere absence was so radical that it would take another 1,000 years for the rest of the world to fully accept it. But here's the thing about 0. The moment you let it into the system, it starts causing problems, not small problems, foundational ones, problems that mathematicians are in a technical sense still arguing about today. The first problem is division. Take any number, divide it by smaller and smaller numbers, and watch what happens. 10 divided by 1 is 10. 10 divided by 1/2 is 20. 10 divided by 1/10 is 100. 10 divided by 100th is 1000. As the number you are dividing by gets closer and closer to 0, the result gets larger and larger without any ceiling. It grows without stopping. It heads, in the language of calculus, toward infinity. So what is 10 divided by 0? The naive answer is infinity. And you can see why someone would say that. The pattern seems to point there. The closer you get to 0 in the denominator, the larger the result. 0 itself should give you infinity, but here's the problem with that answer. Try it from the other direction. Divide 10 by -1/2. You get -20. Divide 10 by -1/10. You get -100. As you approach 0 from the negative side, the result heads toward negative infinity. So which is it? Does 10 divided by 0 equal positive infinity or negative infinity? It cannot be both, and if it is neither, what is it? The answer mathematics settled on is that 10 divided by 0 is undefined. It is not a number. It is not infinity. It is not anything. The operation simply does not produce a result. Division by 0 is not allowed. This sounds like a clean resolution. It is not, because the moment you declare something undefined in mathematics, you have to be extremely careful about what you build on top of that declaration. And it turns out that division by 0 has a way of sneaking into calculations and destroying them from the inside. Here's a classic example. Take two variables, a and b, and set them equal to each other. So a equals b, multiply both sides by a. You get a squared equals a times b, subtract b squared from both sides. You get a squared minus b squared equals a times b minus b squared, factor both sides. The left side factors into the quantity a plus b times the quantity a minus b. The right side factors into b times the quantity a minus b. Now divide both sides by the quantity a minus b. The left side becomes a plus b, the right side becomes b, so a plus b equals b. Since a equals b, substitute b for a on the left side. You get b plus b equals b, which gives you 2b equals b. Divide both sides by b, and you get 2 equals 1. 2 equals 1. From perfectly legitimate-looking algebra, the error is in the step where you divide both sides by the quantity a minus b. Since a equals b, the quantity a minus b equals 0. You divide it by 0, the entire proof is nonsense. But it is carefully constructed nonsense, designed to look like valid algebra every step of the way, and if you are moving quickly, if you are not specifically watching for it, you will not catch it. This kind of trap shows up in real mathematical work, not in textbook proofs designed to illustrate a point, but in actual research, in computer systems, in engineering calculations. A division by 0 hiding inside a longer derivation can produce a result that looks correct, passes initial checks, and then causes catastrophic failure when it hits a real-world application. In 1997, the United States Navy warship USS Yorktown suffered a complete propulsion failure while on exercises in the Atlantic. The ship was dead in the water for nearly 3 hours. The cause was a software system that allowed a crew member to enter 0 into a database field that was later used as a denominator in a calculation. The system divided by 0, crashed and took the entire propulsion network down with it. A billion-dollar warship stopped cold by the oldest problem in arithmetic. But division is only the beginning of what zero does to mathematics. Zero has a strange relationship with exponents. Any number raised to the power of 0 equals 1. 2 to the power of 0 is 1. 1,000,000 to the power of 0 is 1. -7 to the power of 0 is 1. This is a rule, a consistent, universally accepted rule of mathematics. But if you ask most people why, they struggle to give a satisfying answer. The standard explanation goes like this. Consider 2 to the power of 3, which is 8, 2 to the power of 2, which is 4, 2 to the power of 1, which is 2. Each time you decrease the exponent by 1, you divide the result by 2. So 2 to the power of 0 should be 2 divided by 2, which is 1. The pattern demands it. That is a reasonable argument. It is the argument most textbooks give, but notice what it is. It is not a proof from first principles. It is an argument from pattern consistency. We define 2 to the power of 0 as 1 because that definition keeps the rules from breaking. It is a choice, not a discovery. And mathematics is full of these choices, moments where the system could go one of several ways and mathematicians pick the option that caused the least damage. 0 raised to the power of 0 is worse. Some contexts demand it equal 1, others demand it equal 0. Most working mathematicians treat it as 1 for practical purposes, particularly in combinatorics and calculus, where the convention keeps important formulas clean and consistent. But it is not universally agreed upon. It sits in a category called an indeterminate form, which is the mathematical equivalent of saying we know this is a problem and we have agreed to handle it carefully, rather than solve it outright. There are 6 other indeterminate forms that show up in calculus. 0 divided by 0, infinity divided by infinity, 0 times infinity, infinity minus infinity, 1 raised to the power of infinity, 0 raised to the power of 0. Each one of these is a place where the normal rules of arithmetic break down, and you need more sophisticated tools, specifically limits, to figure out what is actually going on. The deepest strangeness of 0 is not in what it does to arithmetic. It is in what it did to mathematics as a whole. Before 0, numbers were things you used to count objects. 1, sheep, 5 soldiers, 12 months. Numbers described the world. 0 broke that model. 0 was not a count of anything. It was the formalization of absence, and once you formalize absence, you open the door to the formalization of other things that do not correspond to physical objects. Negative numbers, imaginary numbers, infinitesimals. The entire apparatus of modern mathematics depends on the willingness to say that a symbol can represent something that does not exist in it. 0 was the first time mathematics made that move. Everything strange that came after it, and a great deal of strangeness did come after it, traces back in some way to that small dot that Brahmagupta wrote down in 6th century India. He probably had no idea what he was starting. Prime obsession. Imagine you are a number, not a complicated number, not a fraction or a negative or an imaginary. Just a clean, positive whole number sitting on the number line somewhere to the right of 0. Now ask yourself one question. Can you be divided? If the answer is yes, if some smaller number other than 1 goes into you evenly, you are composite. You are built from pieces. You have factors. You are, in a sense, not fundamental. But if the answer is no, if the only numbers that divide you evenly are 1 and yourself, then you are something else entirely. You are prime. You are irreducible. You are, in the deepest mathematical sense, an atom. The primes begin simply enough. 2, 3, 5, 7, 11, 13, 17, 19, 23. They feel almost random, scattered across the number line without any obvious pattern. And that feeling of randomness, that sense that the primes are distributed according to some rule that keeps slipping out of view, is not just an impression, it is one of the central unsolved problems in all of mathematics. A problem so deep and so resistant that it has defeated every serious attempt at a solution for over 160 years and currently carries a prize of $1 million for whoever cracks it. But before we get to that, we need to understand why primes matter at all, why mathematicians have been obsessed with them since ancient Greece, why they are not just a curiosity but the structural backbone of the entire number system. The answer is a theorem. One of the oldest and most important theorems in mathematics. It is called the fundamental theorem of arithmetic, and it says this: every whole number greater than 1 is either prime itself or can be expressed as a unique product of prime numbers. 12 equals 2 times 2 times 3, 30 equals 2 times 3 times 5, 100 equals 2 times 2 times 5 times 5. Every number, no matter how large, breaks down into a unique combination of primes, and that combination is the same no matter how you do the factoring. The primes are not just scattered oddities on the number line, they are the building blocks from which every other number is constructed. They are the atoms of arithmetic. Euclid understood this around 300 years before the Common Era. He also proved something else about the primes that seems simple but is not. He proved there are infinitely many of them. His proof is one of the most elegant arguments in all of mathematics, and it takes about 4 sentences. Suppose there are finitely many primes. Write them all down in a list, multiply them all together, and add 1. The resulting number is either prime itself, in which case you have found a prime not on your list, or it is composite, in which case it must be divisible by some prime. But that prime cannot be any of the ones on your list, because dividing by any of them leaves a remainder of 1. Either way, your list was incomplete. Therefore, the assumption that there are finitely many primes is false. There are infinitely many. That proof has stood for roughly 2,300 years. It has never needed revision. It is as solid today as the day Euclid wrote it down. So the primes are infinite. They go on forever. But how are they distributed? How often do they appear as you move further along the number line? Do they keep showing up at roughly the same rate, or do they start thinning out? They thin out. That much was observed early. Among the first 10 numbers, 4 are prime: 2, 3, 5, and 7. That is 40%. Among the first 100 numbers, 25 are prime: 25%. Among the first 1,168 are prime, about 16.8%. Among the first 1,078,498 are prime, about 7.8%. Primes keep appearing, but they get rarer and rarer as the numbers get larger. In 1896, 2 mathematicians, Jacques Hadamard and Charles-Jean de la Vallée-Poussin, independently proved a precise version of this observation. Their result is called the prime number theorem, and it says that the number of primes up to some large number n is approximately n divided by the natural logarithm of n. The natural logarithm is a specific mathematical function, the inverse of raising the number e, approximately 2.718 to a power. The prime number theorem gives you a formula for roughly how many primes exist below any given threshold. This was a monumental achievement, but it was an approximation. It told you roughly how many primes there were. It did not tell you exactly where they were. It did not explain the gaps, the places where primes clustered together, and the places where they spread far apart. It did not touch the deeper question of whether there was any pattern, any order, any structure underlying the apparent randomness of the primes. That question leads directly to Bernhard Riemann. In 1859, Riemann published a single paper on the distribution of prime numbers. It was 8 pages long. It is one of the most important documents in the history of mathematics. In it, Riemann introduced a mathematical function now called the Riemann zeta function. The zeta function takes a complex number as its input, meaning a number with both a real part and an imaginary part, and produces another complex number as its output. Its definition involves an infinite sum. The zeta function evaluated at a complex number s equals the sum of 1 divided by n to the power of s, where n runs over all positive integers from 1 to infinity. Riemann noticed that this function has zeros, places where the input produces an output of exactly 0. Some of these zeros are obvious and uninteresting. They occur at the negative even integers, -2, -4, -6, and so on. Mathematicians call these the trivial zeros, but there are other zeros, infinitely many of them, scattered in a vertical strip of the complex plane where the real part of the input is between 0 and 1. These are the non-trivial zeros. And Riemann looked at the first few of them and noticed something. They all had a real part of exactly 1/2. He could not prove this was always true, but he stated it as a hypothesis. All non-trivial zeros of the Riemann zeta function have a real part of exactly 1/2. That statement is the Riemann hypothesis. It has been checked computationally for the first 10 trillion non-trivial zeros, and they all sit exactly where Riemann predicted, every single one of them, on the line where the real part equals 1/2, and yet no one has proved it. Not in 165 years, not despite the sustained effort of arguably the greatest concentration of mathematical talent in history. not despite the fact that hundreds of other results in number theory have been proved conditionally, meaning they are known to be true if the Riemann hypothesis is true, so that a proof of the hypothesis would instantly unlock a cascade of other theorems. The problem sits there, verified beyond any reasonable empirical doubt, logically undefeated. Why does it matter so much? Because the non-trivial zeros of the Riemann zeta function encode information about the distribution of prime numbers. There is a precise formula developed from Riemann's original paper that expresses the exact count of primes below any given number in terms of these zeros. The zeros are not just an abstract curiosity. They are the frequencies in a kind of musical score that the primes are playing. Understanding the zeros means understanding the primes, and understanding the primes means understanding the deepest structure of arithmetic itself. In 1900, David Hilbert listed the Riemann hypothesis as the 8th problem on his famous list of 23. It is still unsolved. In 2000, the Clay Mathematics Institute listed it as one of 7 Millennium Prize problems, each carrying a reward of $1 million. 6 of the 7 remain unsolved. The Riemann hypothesis is one of them. There is one more thing about primes worth sitting with. Twin primes. A twin prime is a pair of primes that differ by exactly 2, 3 and 5, 5 and 7, 11 and 13, 17 and 19, 29 and 31. They keep appearing. As you go further and further along the number line, you keep finding pairs of primes separated by just 2. The twin prime conjecture says this goes on forever, that there are infinitely many twin prime pairs. It has never been proved. In 2013, a mathematician named Yitang Zhang, who was largely unknown at the time and was working as a lecturer at the University of New Hampshire, published a proof that there are infinitely many pairs of primes separated by at most 70 million. That was the first finite bound ever established. It did not prove the twin prime conjecture, but it was the first time anyone had proved that prime pairs with any fixed finite gap keep appearing forever. The mathematical community was stunned. Zhang had been working on the problem quietly for years with almost no support and no expectation from the broader field that a breakthrough was coming. Since Zhang's paper, other mathematicians have worked to reduce that bound. It currently sits at 246, meaning it has been proved that there are infinitely many pairs of primes separated by at most 246. The target is 2. No one is there yet. The primes remain, after more than 2,000 years of sustained attention, fundamentally mysterious. We know they are infinite. We know roughly how they are distributed. We have powerful tools for finding and working with them, and we cannot predict where the next one will be, cannot prove the most basic conjecture about their pairing behavior, and cannot crack the central hypothesis that would unlock our deepest understanding of their structure. Irrational realities. Do you know what it can be like to pretend to be a Pythagorean? Not in the loose modern sense of someone who uses the Pythagorean theorem to calculate distances, in the full, committed, almost religious sense. You are a member of a school of thought founded by Pythagoras of Samos in the 6th century before the Common Era, and you believe genuinely and deeply that number is the foundation of all reality, that the universe is built from whole numbers and their ratios, that music, geometry, astronomy, and the structure of existence itself can be expressed as relationships between integers, that everything, without exception, reduces to a fraction. This is not a casual belief, it is a cosmology. It is a complete account of what the universe is made of and how it works, and it is about to be destroyed by a square. The square in question has sides of length 1, a unit square, the simplest possible square, and the question is equally simple. How long is the diagonal? The Pythagorean theorem, which the Pythagoreans knew and used, gives you the answer immediately. The diagonal d satisfies d squared equals 1 squared plus 1 squared, which means d squared equals 2, which means d equals the square root of 2. Clean, mechanical, straightforward, except for one problem. The square root of 2 is not a fraction. This is not obvious. It does not feel like it should be true. There are fractions that get very close. 7 divided by 5 is 1.4. 17 divided by 12 is approximately 1.4167. 985 divided by 696 is even closer. You can keep finding fractions that approach the square root of 2 with increasing precision, but you can never find one that lands exactly on it, because the square root of 2 is irrational. It cannot be expressed as a ratio of two whole numbers. Its decimal expansion goes on forever without repeating. 1.414, 21356237309504888 and so on, forever, without pattern, without repetition, without end. The proof that the square root of 2 is irrational is one of the oldest proofs in mathematics and one of the most beautiful. It proceeds by contradiction. Assume the square root of 2 is rational, then it can be written as a fraction p divided by q, where p and q are whole numbers with no common factors. They are in lowest terms. Square both sides. 2 equals p squared divided by q squared. Multiply both sides by q squared. 2 times q squared equals p squared. This means p squared is even, and if p squared is even, then p itself must be even, because if p were odd, p squared would be odd. So write p as 2 times k for some whole number k. Substitute back in. 2 times q squared equals 2k times 2k, which equals 4k squared. Divide both sides by 2. Q squared equals 2k squared. This means q squared is even, which means q is even, but now both p and q are even. That contradicts the assumption that they had no common factors. The assumption is false. The square root of 2 is irrational, according to ancient accounts. This proof was discovered by a Pythagorean named Hippasus of Metapontum. The story goes that he discovered it while at sea, possibly while trying to work out a geometric problem, and according to those same accounts, his fellow Pythagoreans were so disturbed by the result, so threatened by the implication that the universe contained quantities that could not be expressed as ratios of whole numbers, that they threw him overboard and drowned him. This story is almost certainly embellished, but the mathematical crisis it represents was entirely real. The discovery of irrational numbers did not just complicate Pythagorean philosophy, it invalidated it. If the diagonal of a unit square cannot be expressed as a ratio, then the belief that all of reality reduces to ratios of integers is simply wrong. The universe contains quantities that the Pythagorean number system cannot reach. The foundation cracked, and the square root of 2 was just the beginning. The square root of 3 is irrational. The square root of 5 is irrational. The square root of any whole number that is not a perfect square is irrational. The cube root of 2 is irrational. These results follow from proofs similar to the one above, with slight modifications. There are, it turns out, vastly more irrational numbers than rational ones, in the precise technical sense established by Cantor's work on infinite sets discussed in the previous segment. The rational numbers, all the fractions, all the integers, form a set of size Aleph null. The irrational numbers form a set with the cardinality of the continuum, a strictly larger infinity. If you pick a random point on the number line, the probability that it is rational is, in a well-defined technical sense, exactly 0. The number line is almost entirely made of numbers that cannot be written as fractions. But within the irrationals, there is a further distinction, and this is where the strangeness deepens considerably. Some irrational numbers are what mathematicians call algebraic. An algebraic number is one that is the solution to some polynomial equation with integer coefficients. The square root of 2 is algebraic because it solves the equation x squared minus 2 equals 0. The square root of 3 is algebraic because it solves x squared minus 3 equals 0. The cube root of 5 is algebraic because it solves x cubed minus 5 equals 0. These numbers cannot be written as fractions, but they can be pinned down as the solutions to equations. They are irrational, but they are reachable through algebra. Then there are numbers that are not even algebraic. Numbers that are not the solution to any polynomial equation with integer coefficient, no matter how complicated the polynomial. These numbers are called transcendental, and their existence was not even suspected until the 19th century, and not proved until 1844, when a mathematician named Joseph Liouville constructed the first explicit example of a transcendental number. The most famous transcendental numbers are ones you already know. Pi is transcendental. The number e, the base of the natural logarithm, approximately 2.71828, is transcendental. These are not just irrational. They are beyond the reach of algebra entirely. No polynomial equation with integer coefficients will ever produce pi as a solution. No matter how many terms you add, no matter how large the coefficients get, pi sits outside the entire algebraic universe. The proof that pi is transcendental, produced by Ferdinand von Lindemann in 1882, had an immediate and dramatic consequence. It settled once and for all one of the oldest problems in mathematics, squaring the circle. Squaring the circle was a problem posed in ancient Greece. Given a circle, construct a square with exactly the same area using only a compass and a straight edge. No measurement, no calculation, just geometric construction. Mathematicians had been attempting this for roughly 2,000 years. Lindemann's proof that pi is transcendental ended the search immediately. A compass and straightedge construction can only produce algebraic numbers. Pi is not algebraic, therefore squaring the circle is impossible. Not difficult, not currently beyond our techniques, impossible. Provably, permanently, mathematically impossible. 2,000 years of effort, closed by 4 letters. Pi is transcendental. There is one more layer to this story, and it is the one that should probably keep you up at night. We know that transcendental numbers exist. We know that pi and e are among them. We know that transcendental numbers are, in the same sense that irrational numbers overwhelm rationals, far more common than algebraic numbers. Almost every real number is transcendental. The algebraic numbers are a vanishingly small minority of the number line, and yet we can only explicitly identify a tiny handful of them. The reason is this: to prove a specific number is transcendental, you need a proof, a rigorous mathematical argument that this particular number cannot be the root of any polynomial with integer coefficients. Those proofs are extraordinarily difficult. We know pi is transcendental. We know e is transcendental. We do not know whether pi plus e is transcendental. We do not know whether pi times e is transcendental. We do not know whether pi to the power of e is transcendental. We do not know whether e to the power of pi squared is transcendental. These are not obscure combinations of exotic constants. They are the simplest possible arithmetic operations applied to the 2 most famous transcendental numbers in mathematics, and we cannot prove transcendence for any of them. We are surrounded by transcendental numbers. The number line is almost nothing but transcendental numbers, and we can name almost none of them with certainty. The Pythagoreans wanted a universe made of clean ratios. What they got instead was a number line so full of unreachable, unnameable, algebraically invisible quantities that the numbers we can actually work with are, in a precise mathematical sense, a set of measure 0, a negligible fraction of the whole. Imaginary dimensions. Imagine you are Girolamo Cardano. It is the year 1545. You are a mathematician, physician, and compulsive gambler living in Milan, and you have just published a book called Ars Magna, which translates roughly as the Great Art. It is one of the most important algebra textbooks ever written. In it you present, among other things, a general method for solving cubic equations, meaning polynomial equations where the highest power of the variable is 3. This is a significant achievement. Mathematicians had been trying to crack the cubic for centuries. You have done it. But in working through the method, you have encountered something that makes you deeply uncomfortable. In certain cases, the procedure requires you to take the square root of a negative number, not as a final answer. The final answers come out as ordinary numbers, but as an intermediate step, sitting in the middle of the calculation, there is a square root of a negative number, and you have no idea what that means. You write about it in the book. You call these quantities sophistic and useless. You note that the method works, that the answers are correct, but that the intermediate steps involve numbers that seem to be purely fictitious. You perform the calculation, get the right answer, and then essentially shrug. The thing works, but you cannot explain why, and the objects it requires you to manipulate do not correspond to anything you can point to or measure. That discomfort, that sense of a mathematical object that exists in the calculations but nowhere else, persisted for over 2 centuries, and then, slowly, it didn't. The imaginary numbers stopped being embarrassment and became one of the most powerful tools in all of mathematics and physics, and the path from Cardano's discomfort to that power is one of the strangest stories in the history of human thought. Start with the problem itself. In ordinary arithmetic, squaring any real number gives you a positive result. 2 squared is 4. Negative 2 squared is also 4. There's no real number whose square is negative 1. The square root of negative 1 does not exist on the real number line. It is not to the left of 0, or to the right of 0, or at 0. It is simply not there. Mathematicians eventually decided to stop treating this as a problem and start treating it as a definition. Define a new number, call it I, and declare that I squared equals negative 1. Do not ask what I is or where it lives. Just accept the definition and see what happens when you build mathematics on top of it. What happens is extraordinary. Take any real number and multiply it by I. You get an imaginary number, 2 times I, negative 7 times I pi times I. These are imaginary numbers, real numbers scaled by I. Now take a real number and add an imaginary number to it. 3 plus 2i, negative 1, plus pi times I, 5 plus 0 times I, which is just 5. These are complex numbers. Numbers with a real part and an imaginary part, written in the form of plus b times I, where a and b are both real numbers. The complex numbers contain the real numbers as a special case, when the imaginary part b equals 0. but they are a larger system, a two-dimensional system, and this is the first genuinely strange thing about them. Real numbers live on a line. Complex numbers live on a plane. The moment you introduce I, you have expanded the number system from one dimension to two. The number line becomes the number plane. This is not just a metaphor. It is literally true in a geometric sense. If you draw a horizontal axis and label it with real numbers, and then draw a vertical axis perpendicular to it and label it with imaginary numbers, every complex number corresponds to exactly one point on that plane. The number 3 plus 2i sits 3 units to the right and 2 units up. The number -1 minus I sits 1 unit to the left and 1 unit down. The entire plane is filled with complex numbers, one at every point. And once you have that picture, something remarkable becomes visible. Multiplying by I does not just scale numbers, it rotates them. Multiply any complex number by I, and the point it corresponds to on the plane rotates 90 degrees counterclockwise around the origin. Multiply by I again another 90 degrees. Multiply by I twice, and you have rotated 180 degrees. You have multiplied by I squared, which equals -1. Multiplying by -1 flips a number to the other side of 0 on the number line. Rotation by 180 degrees does the same thing geometrically. The algebra and the geometry are saying exactly the same thing in two different languages. This connection between complex multiplication and rotation is not a curiosity. It is the engine behind a large portion of modern physics and engineering. Electrical engineers use complex numbers to analyze alternating current circuits, because the rotation interpretation captures the behavior of oscillating quantities cleanly and efficiently. Signal processing, the mathematics behind your phone, your radio, your wireless internet, runs on complex numbers. Quantum mechanics, the deepest physical theory we have, is written in the language of complex numbers. The wave function that describes the state of a quantum system is a complex valued function. Without complex numbers, quantum mechanics, as we know it, does not exist. But before any of that, there is a formula. The most famous formula in mathematics, according to polls of mathematicians conducted at various points over the last century, it is called Euler's identity, after the Swiss mathematician Leonhard Euler, who derived it in the 18th century. It states that e to the power of I times pi plus 1 equals 0. 5 numbers, e approximately 2.71828, the base of the natural logarithm. I, the square root of -1. Pi, approximately 3.14159, the ratio of a circle's circumference to its diameter. 1, the multiplicative identity. 0, the additive identity. 5 of the most fundamental constants in all of mathematics, connected by a single equation involving addition, multiplication, and exponentiation. The formula comes from a more general result called Euler's formula, which states that e to the power of I times x equals the cosine of x plus I times the sine of x. This formula connects exponential functions, which describe growth and decay, to trigonometric functions, which describe oscillation and rotation. These were before Euler considered to be entirely separate branches of mathematics with no deep connection to each other. Euler's formula reveals that they are the same thing viewed from different angles. Literally, the cosine and sine functions describe the horizontal and vertical components of rotation around a circle. The exponential function describes growth along a line. Complex numbers show that these are two descriptions of a single underlying reality. Set x equal to pi in Euler's formula. The cosine of pi is -1. The sine of pi is 0. So e to the power of I times pi equals -1 plus I times 0, which equals -1. Add 1 to both sides. E to the power of I times pi plus 1 equals 0. There it is. Mathematicians describe Euler's identity as beautiful. That word gets used a lot in mathematics, and it can sound like hyperbole. In this case, it is not. The identity is beautiful in the same way a Bach fugue is beautiful. It reveals that things which appeared to be separate are secretly the same. It compresses an enormous amount of mathematical structure into a single line. It is surprising even after you understand the proof. Something about it continues to feel like it should not be true, and the gap between that feeling and the certainty that it is true is where the beauty lives. Now go back to Cardano and his discomfort. He encountered the square root of -1 in 1545 and called it sophistic and useless. What he had actually stumbled across was the gateway to a two-dimensional number system that would turn out to be the natural language of rotation, oscillation, and wave behavior. A system so fundamental to physics that it appears at the deepest level of our description of matter and energy, a system that produces, as a byproduct of its internal logic, the most celebrated equation in all of mathematics. He had no way of knowing any of that. He just knew the calculation worked and the intermediate steps made no sense, which is, if you think about it, a reasonable description of how a large portion of mathematical discovery actually goes. You follow the rules, you get a result that works, and you spend the next 2 centuries figuring out why. There is one more thing worth noting. The complex numbers are, in a precise technical sense, complete. Every polynomial equation with complex coefficients has all of its solutions inside the complex numbers. You do not need to invent anything new. This result is called the fundamental theorem of algebra, and it means that the step from real numbers to complex numbers is the last step. The system closes. No matter what polynomial you write down, no matter how complicated, all of its roots exist somewhere on the complex plane. The real numbers are missing things. The square root of -1 is not there, but the complex numbers are missing nothing. Every equation that should have a solution has one. The 2-dimensional number plane is, algebraically speaking, perfect, which raises an obvious question. If 1 dimension is incomplete and 2 dimensions are complete, what happens in 3 dimensions? What is a 3-dimensional number system? The answer is that it does not exist. You can go from 1 dimension to 2. The next step takes you to 4, not 3. 4-dimensional numbers called quaternions were discovered by the Irish mathematician William Rowan Hamilton in 1843. He had been trying to construct 3-dimensional numbers for years and failing. The answer, when it finally came to him while walking across a bridge in Dublin, was that 3 dimensions do not work. The algebra breaks. 4 dimensions do. He was so excited by the realization that he carved the defining equations into the stone of the bridge with his penknife. The equations he carved were I squared equals j squared equals a times j times k equals -1. 4 dimensions. 3 imaginary units, a number system where multiplication is not commutative, meaning I times j does not equal j times I. A system strange enough to make the complex numbers look straightforward by comparison. Cardano looked at the square root of -1 and saw an embarrassment. What was actually there was the first step into a tower of number systems that goes from the real line to the complex plane to the 4-dimensional quaternions, each one stranger and more powerful than the last, each one discovered by someone willing to follow the mathematics into territory that had no visible connection to physical reality, and each one turning out eventually to describe physical reality with uncanny precision. Probabilities lies. You are standing in a casino in Monaco in the summer of 1913. You are watching a roulette wheel. The wheel has been spinning for a while and you have been keeping track of the results. Black has come up 26 times in a row. 26 consecutive spins, all black. The crowd around the table has grown dense. People are betting heavily on red. The logic seems airtight. Red is overdue. The universe owes the table a red. The probability of 27 blacks in a row is astronomically small. Something like 1 in 137 million. You would be irrational not to bet red right now. You would also be wrong. The roulette wheel does not know it has landed on black 26 times in a row. It has no memory. Each spin is independent of every other spin. The probability of red on the next spin is exactly what it always is, just under 50%, accounting for the green 0 slots. It was just under 50% before the streak started. It is just under 50% now. The 26 previous results are irrelevant. They do not accumulate. They do not create debt. They do not influence the wheel in any way whatsoever. The crowd lost a great deal of money that night. The streak ended at 26. Red came up eventually, as it always does eventually. But the people who had been betting red from spin 15 onward, convinced that the laws of probability were building toward a correction, had already been cleaned out. This mistake has a name. It is called the gambler's fallacy, and it is one of the most persistent and costly errors in human reasoning. But it is also, if you look at it carefully, a window into something deeper and stranger about probability itself. Because probability is one of those areas of mathematics where the results are not just counterintuitive, they are actively hostile to human intuition. The way we naturally think about chance is wrong in ways that are systematic, repeatable, and surprisingly difficult to correct, even when you know about them. Start with a problem that is simple enough to state in one sentence, but has caused more arguments among mathematicians, statisticians, and probability theorists than almost any other puzzle in the field. It is called the Monty Hall problem, named after the host of a mid-20th century American game show called Let's Make a Deal, and it goes like this. You are a contestant on a game show. There are 3 doors. Behind one of them is a car. Behind the other 2 are goats. You pick a door, say door number 1. The host, who knows what is behind every door, opens one of the other two doors to reveal a goat, say door number 3. He then offers you a choice. You can stick with door number 1 or switch to door number 2. What should you do? Most people say it does not matter. There are 2 doors left. One has a car, one has a goat. It is 50-50. Switching gains you nothing. This is wrong. You should always switch. Switching wins the car 2/3 of the time. Sticking wins only 1/3 of the time. The reasoning goes like this. When you first picked door number 1, the probability that the car was behind one of the other 2 doors was 2/3. When the host opens door number 3 to reveal a goat, that 2/3 probability does not disappear. It collapses entirely onto door number 2. The host has given you information. He has not just randomly opened a door, he has specifically opened a door he knows contains a goat. This act of informed selection shifts the probabilities. Door number 2 now carries a 2/3 chance of hiding the car. When this solution was published in a popular magazine column in 1990 by a writer named Marilyn Vos Savant, the response was extraordinary. Approximately 10,000 readers wrote in to tell her she was wrong. Many of them were mathematicians and statisticians with advanced degrees. Several were PhDs from prestigious institutions. The letters were not polite. They were contemptuous. One wrote that her error was so fundamental it was embarrassing to the profession. Another suggested she should admit her mistake and get on with her life. She was right. Every single one of them was wrong. The reason the Monty Hall problem is so difficult, the reason it trips up mathematicians who should know better, is that it requires you to track information carefully. The host's action is not random. It is constrained by knowledge. He cannot open the door you picked. He cannot open the door with the car. This constraint means his action tells you something, and that something shifts the probabilities in a non-obvious direction. Our intuition treats his action as random and therefore uninformative. It is not random, therefore it is informative, and the information it carries is worth 2/3 of a car. But the Monty Hall problem, strange as it is, at least has a clean resolution. You can simulate it, run it 10,000 times, and the 2/3 result will emerge from the data with complete reliability. It is counterintuitive, but it is not paradoxical. Probability gets stranger than that. Consider the birthday problem. How many people do you need in a room before there is a greater than 50% chance that 2 of them share a birthday? Most people guess somewhere in the range of 180 to 200. The actual answer is 23. With just 23 people in a room, the probability that at least 2 of them share a birthday exceeds 50%. With 57 people, it exceeds 99%. The reason the intuitive estimate is so far off is that people think about the problem the wrong way. They imagine checking whether anyone shares a birthday with them specifically. That probability does indeed require a large group, but the birthday problem asks whether any 2 people in the room share a birthday with each other. The number of possible pairs in a room of 23 people is 253. Each pair has roughly a 1 in 365 chance of sharing a birthday. With 253 independent chances, the cumulative probability climbs quickly above 50%. The problem is about pairs, not about you specifically. Intuition gets the problem wrong because it personalizes a question that is actually about combinations. Now go deeper. Consider what probability actually is. This sounds like a strange question. Probability is the likelihood of an event. It is a number between 0 and 1. Simple, but when you push on the foundations, the concept fractures in ways that have produced genuine, sustained, unresolved disagreement among mathematicians and philosophers for over a century. There are 2 main interpretations. The frequentist interpretation says that the probability of an event is the limit of its relative frequency over a very large number of trials. The probability of a fair coin landing heads is 1/2 because if you flip it an enormous number of times, approximately half of those flips will be heads. Probability is a property of repeatable processes. It is defined by what happens in the long run. The Bayesian interpretation says that probability is a measure of degree of belief. It is a quantification of how confident you are in a proposition given the evidence available to you. On this view, it makes perfect sense to assign a probability to a one-time event, to a historical fact, to a scientific hypothesis. Probability is not about frequencies in the long run. It is about rational belief in the present. These 2 interpretations give different answers to real problems. They disagree about how to analyze scientific experiments, how to interpret statistical evidence, how to update beliefs in light of new data. The disagreement is not academic. It influences how medical trials are designed and interpreted, how courts evaluate forensic evidence, how artificial intelligence systems are built. And it has not been resolved. Frequentists and Bayesians have been arguing since the 19th century. Both camps contain brilliant mathematicians. Both have produced powerful methods. Neither has defeated the other. There is a result that captures the strangeness of probability more sharply than almost anything else. It is called Borel's paradox, and it concerns conditional probability on continuous distributions. Take a sphere. Pick a random point on its surface. What is the probability that the point lies on the equator? 0, because the equator is a one-dimensional curve on a two-dimensional surface, and in a continuous uniform distribution, any specific curve has probability 0. Fine. Now condition on the point lying on a specific meridian, a line of longitude. Given that the point is on that meridian, what is the probability it lies at the intersection of the meridian and the equator? The answer depends on how you parameterize the problem. Different mathematically valid approaches give different answers. The conditional probability is not well defined without specifying the method of conditioning. This is not a paradox in the sense of a logical contradiction. It is a paradox in the deeper sense that a concept we think we understand, conditional probability, turns out to be ambiguous in ways that only become visible in continuous settings. The mathematics of probability, when pushed to its foundations, contains genuine subtleties that the intuitive picture of chance and likelihood completely fails to capture. And then there is quantum mechanics, where probability stops being a description of our ignorance and becomes, if the standard interpretation is correct, a fundamental feature of reality itself. In classical physics, probability enters because we do not have complete information. The coin flip is determined by physics. If we knew the exact force applied, the exact air resistance, the exact surface properties, we could predict the outcome with certainty. Our use of probability reflects our ignorance, not any genuine randomness in nature. In quantum mechanics, this does not appear to be true. The decay of a radioactive atom is not determined by hidden variables we have failed to measure. According to the best physical theory we have, there is no fact of the matter about when the atom will decay until it decays. The probability is not a measure of our ignorance. It is a measure of genuine, irreducible fundamental indeterminacy built into the fabric of the universe. Whether this is actually true, whether quantum mechanics is telling us that reality is genuinely probabilistic at its core, or whether there is a deeper deterministic theory waiting to be discovered, is one of the most contested questions in the foundations of physics. It has been contested since the 1920s. Einstein famously refused to accept that God plays dice with the universe. Most physicists today believe he was wrong about this, but the question has not been experimentally settled in a way that everyone finds convincing. Probability began as a tool for analyzing games of chance. It became the language of statistics, of science, of decision theory, of artificial intelligence, and eventually of our deepest theory of physical reality. At every step, it turned out to be stranger than it looked. The gambler in Monaco in 1913 thought probability was simple. It told you what to expect. It created obligations, debts, corrections. Red was overdue. Geometry breaks. Picture yourself as Euclid. It is around 300 years before the Common Era. You are in Alexandria, working in or around the greatest library the ancient world ever produced, and you are doing something that has never quite been done before. You are not just doing mathematics, you are organizing it. You are taking the accumulated geometric knowledge of the ancient world, everything the Egyptians measured, everything the Greeks proved, everything that had been discovered piecemeal over centuries, and you are building it into a single unified system from the ground up. The system works like this. You start with a small number of definitions. A point is that which has no part. A line is breadthless length. You add a small number of common notions, things so obvious they need no proof. Things equal to the same thing are equal to each other. If you add equal things to equal things, the results are equal. And then you state 5 postulates, 5 assumptions about the nature of geometric space that you're going to take as given. Without proof as the foundation, everything else will be built on. The first 4 postulates are clean and simple. You can draw a straight line between any 2 points. You can extend a line indefinitely. You can draw a circle with any center and any radius. All right angles are equal to each other. These feel inevitable. They feel like the kind of things that could not possibly be otherwise. They feel less like assumptions and more like observations about the obvious nature of space. Then there is the 5th postulate. If a straight line crosses 2 other straight lines and creates interior angles on one side that sum to less than 2 right angles, then those 2 lines, if extended far enough, will meet on that side. Read that again. It is longer. It is more complicated. It has a conditional structure that the other 4 postulates do not have. It feels different. It feels to modern readers, and it apparently felt to ancient readers as well, like it should be provable from the other 4, rather than assumed independently. It feels like a theorem pretending to be an axiom. For roughly 2,000 years, mathematicians tried to prove it, not because they doubted it was true. Euclid's geometry matched physical space perfectly, as far as anyone could measure, but the fifth postulate felt unearned. It felt like it was sneaking in more than it should be allowed to assume. If you could derive it from the first four postulates, the system would be cleaner, tighter, more satisfying. Everyone failed, not for lack of effort. Some of the greatest mathematical minds across 2 millennia took runs at this problem. Every single one of them either produced an argument with a hidden flaw or eventually admitted defeat. And the reason they all failed is not that they were not clever enough. It is that the fifth postulate is independent of the other four. It cannot be proved from them. And the proof of that independence, when it finally came in the early 19th century, did not just solve a 2,000-year-old problem, it shattered the idea that there is only one possible geometry. Here's how the independence was demonstrated. 3 mathematicians working in different countries with limited awareness of each other's work arrived at essentially the same idea within a few decades of each other. Their names were János Bolyai, a Hungarian army officer who published in 1832, Nikolai Lobachevsky, a Russian mathematician who published around the same time, and Carl Friedrich Gauss, who is widely considered one of the greatest mathematicians in history, who worked out the same ideas privately and never published them, apparently because he feared the controversy. Their idea was this: instead of trying to prove the fifth postulate, assume it is false. Specifically, assume the alternative where, given a line and a point not on that line, there is more than one line through that point that is parallel to the original line. In Euclid's geometry, there is exactly one such parallel line. That is essentially what the fifth postulate guarantees. Bolyai and Lobachevsky asked what happens if there are infinitely many. They expected to derive a contradiction. If the fifth postulate follows necessarily from the first four, then assuming its negation should produce nonsense. Something should break. 2 theorems should contradict each other. The system should collapse. It did not collapse. They built an entirely consistent geometry on the alternative assumption, a geometry where the angles of a triangle sum to less than 180 degrees, a geometry where parallel lines diverge as they extend, a geometry where the circumference of a circle grows faster than pi times the diameter, a geometry that violates every spatial intuition trained by a lifetime of living in what feels like Euclidean space. And it was perfectly, rigorously, unbreakably consistent. No contradictions, no paradoxes. A complete alternative geometry, as logically sound as Euclid's, built on a different foundation. This result, which mathematicians call hyperbolic geometry, was deeply unsettling to many of Gauss's contemporaries. If there is more than one consistent geometry which one describes actual physical space, Euclid's geometry had been considered not just a mathematical system, but a description of reality. Kant had argued that Euclidean geometry was a necessary feature of human perception, something built into the structure of how we experience space. The existence of a consistent non-Euclidean geometry did not just challenge Euclid, it challenged Kant. It challenged the idea that mathematical axioms could tell you anything certain about the physical world. Then in 1854, Bernard Riemann, the same Riemann whose hypothesis about prime numbers we discussed in the previous segment, gave a lecture that took the situation even further. Riemann generalized the entire framework of geometry. He asked not just what happens if you change the parallel postulate, but what happens if you allow the geometry of space to vary from point to point. What if space is not uniform? What if its curvature changes depending on where you are? Riemann developed the mathematical machinery to describe curved spaces of any number of dimensions. His framework, now called Riemannian geometry, allows you to define distance, angle, and curvature on any smooth surface or higher dimensional analog. It is an enormously flexible and powerful system. At the time, it seemed like pure abstraction, beautiful mathematics with no obvious physical application. There was no reason to think that physical space was anything other than flat and Euclidean. All measurements, all experiments, all physical intuition pointed to flatness. Riemannian geometry was a mathematical toy, impressive but disconnected from reality. Then, 60 years later, Albert Einstein used it to describe gravity. Einstein's general theory of relativity, published in 1915, is built entirely on Riemannian geometry. The core idea is that massive objects curve the fabric of spacetime, and that what we call gravity is not a force pulling objects toward each other, but the curvature of spacetime directing objects along paths called geodesics, the curved space equivalents of straight lines. The mathematics required to express this idea precisely is exactly the mathematics Riemann developed in 1854 for no physical reason at all. Einstein did not invent new mathematics. He reached for the mathematics that was already there, built by someone who had simply been following the logic of geometry without any physical application in mind. The angles of a triangle in the space-time around a massive object do not sum to 180 degrees. Space near a black hole is not Euclidean. The universe at the largest scales and in the most extreme conditions is described by a geometry that Euclid never imagined and that most 19th century mathematicians considered a theoretical curiosity. But there is a third branch of non-Euclidean geometry worth mentioning because it is the one closest to everyday experience. Spherical geometry, or elliptic geometry, is the geometry of the surface of a sphere. On a sphere, the shortest path between 2 points is not a straight line, but a great circle, the kind of arc that airplanes follow when traveling long distances. On a sphere, there are no parallel lines. Any 2 great circles intersect, and the angles of a triangle sum to more than 180 degrees. A triangle drawn on the surface of the Earth with 1 vertex at the North Pole and 2 vertices on the equator has 2 right angles at the equator plus whatever angle exists at the pole. The sum exceeds 180 degrees by an amount that depends on the size of the triangle. You live on a sphere. You have spent your entire life doing geometry on a non-Euclidean surface. The flat maps in your classroom were distortions, attempts to project spherical geometry onto a flat page, and every such projection introduces errors. Greenland appears roughly the same size as Africa on a standard Mercator projection map. Africa is actually about 14 times larger. The geometry you were taught in school is an approximation. A very good approximation for small scales for the distances relevant to everyday human experience. But an approximation nonetheless. Here is the deepest implication of all of this. Euclid built his system on 5 postulates and believed, or at least worked as if he believed, that those postulates described the one true geometry of space. What 2,000 years of subsequent mathematics revealed is that the postulates are choices. Different choices produce different geometries. All of them are internally consistent. All of them are in the technical sense equally valid. The question of which one describes physical space is not a mathematical question at all. It is an empirical question, one that has to be answered by measurement and experiment, not by logic alone. Mathematics can give you an infinite variety of consistent geometric systems. It cannot tell you which one the universe chose to live in. That boundary between what mathematics can determine internally and what requires contact with physical reality is one of the most important and least discussed lessons in the entire history of the subject.